Okay, we're going to take a look at Chester's churros just one more time, but this time it's going to be a different random sample of churros. So each time we take a sample, the result will be a different group of 10 churros, and therefore the sample mean will be different. So let's take a look at the same claim. So first, Chester advertises that his churros have a mean of 300 calories, and we take a sample of 10 churros. So there's our N. The sample mean is found to be 305 this time. Last time it was 320, so this time it's 305. Based on this sample, you're going to look for some claim being made, and the claim is about mu, the population proportion. That parameter is greater than, so we're looking for some kind of comparison words like greater or less or different, is greater than 300 calories. And then you have to be provided with a significance level of the test, so 10% again. And if they give you the population standard deviation sigma, that is what allows us to work with z-scores. So we'll be able to use our z-test. So I went ahead and wrote the hypotheses the same as before. So there's our claim. And again, right tail test, anytime it's a greater than, that's a right tail test. So it can't hurt to be a little repetitive here, right tail test. And so the given values are mu naught is 300. They took a sample of 10 churros. The sample mean came out to be 305. That's bar. They chose alpha to be 10%, 0.10, and sigma, population standard deviation, of 30. Okay, so whether we do the traditional method or the p-value method, usually you would not do both. We are doing it because you're learning both methods, but usually pick a method. Both methods require you to know a test value, and so that's why I do this here. So the test value, again, it will also be called a test statistic. So those are the same thing. So I'm going to do test value for our abbreviation, and then that z-score is the one that corresponds to our sample mean. So I gave you the formula for it, but we can just run the z-test and have the calculator help us out because, so it's going to be a z-test because sigma is known. You might be able to guess that if we didn't know sigma and we knew sample standard deviation, then we wouldn't do z-test, we would do t-test. So we would be following the rules from the confidence interval chapter, but we know sigma, so that's why we're doing a z-test. So we're going to go ahead and let the calculator do that for us. You do not have to do a by hand calculation, even if Alex shows it. So I've gone ahead and entered those values. And the direction of the test again is greater, so greater, mu greater than the mu naught number. And then we'll go with calculate. And the z-score that you see is your test value. We'll go ahead and round that to 2 places. So that's 0.53. And you want to be really careful to see that z-scores are not percents. So sometimes when I round to 2 places, you might think that this is equivalent to 53%. But z-scores have nothing to do with proportions. Z-scores are just numbers on the number line. So z-scores are just going to be somewhere on this number line, and we'll be graphing that value in just a second. So there's our z-score. All right, so the traditional method identifies critical values and critical regions, and it's always based on the significance level of the test. So for a right tail test, the area to the right, I'm going to put it up here, the area to the right for traditional method, the area right of the critical value is your alpha. But we know that to use inverse norm, we need the area left of it. So 1 minus the area to the left of it plus the area to the right of it. And we did all this, that z-score, and we inverse norm that 0.90, that's where we got 1.28. So I just wrote the rule for you here. So if it's a right tail test, we always inverse norm, and it had to be 1 minus our alpha, because that would be the area to the left of it, and that gives you your critical value. All right, and I'm going to go ahead then and draw that picture. I change my color here. So my critical value, Alex will just give you the number 1.28. And sometimes it identifies it using that other notation, z subscript alpha, because the critical value for a right tail test is the value that puts an area to the right of it equal to alpha. So that's why it's called z alpha, but we can just say critical value, totally fine. So that's 10%. So that area is 10%. And the z-scores in that region make up the critical region, and we'll just abbreviate it CR. So z-scores in the shaded part are in the critical region, and then the other z-scores in the unshaded part would be in what we would call the non-critical region. We'll just go NCR. So that's everything in terms of z. And then if we're thinking about means, mu, if the null is true, 300 would be there. All right, so here's how the traditional method works. You establish your critical region, and then you ask yourself, where did the test value fall? Where was it located? So our test value, I'm going to add something up here next to that. That test value corresponds, the calculator did the work, I lost my words. It calculated the z-score that corresponded to the x bar value of 305. So we didn't do it by hand, the calculator did it for us, but we entered the x bar and it gave us its z-score. All right, so first let's graph the z-score. So 0.53, so that would be in here somewhere. It doesn't have to be perfect at all. This is my test value, 0.53. So what that does is tell me that x bar would be right there, 305. So we're getting the test value, so we know where the x bar is, which means that that 305, while it is greater than 300, it did not make it out into the shaded critical region. So it's larger, but not large enough to really make me believe that 300 is incorrect. So that's hypothesis testing. We look at our sample, and if we get something really far away, really unusual, if that's the mean, then we would reject the mean is 300. But 305 is not significantly bigger than 300. So it's not far enough away to really convince me, because 305 happens quite frequently, right? It's here in the middle part of this graph. So that's how it works. We say that where is our test value? So if our test value falls in our non-critical region, so my unshaded region, then we would say we fail to reject the null, or we say we do not reject the null. We do not reject the null hypothesis, which is H naught. So the language is always, do we reject it like we did last time, or do we fail to reject it, or don't reject it? So you can say do not reject it, or sometimes we say fail to reject it. But we're always addressing that word reject. Do we reject or not? So in this case, then, if we don't reject it. We just don't have enough evidence to reject it. That means that we don't have enough evidence to support our claim. So if we don't reject the null, we don't support our claim. Last time, we did reject the null and we did support our claim. All right, so that we're done with the traditional method. 305, we would say it's not statistically significant. So it does not make it into our critical region. All right, then we just start fresh. So let's pretend we didn't do that method, and instead we chose to do the p-value method. And we're looking at them to see how they're related, but it would be just starting the problem and going straight p-value method. So in the p-value method, the only thing we graph is our test value. So I'm going to go to my test value. So that test value, not T0, sorry, my test value 0.53 told me that X bar would be right there. So those line up. 300 would be there. And a p-value stands for probability. So it's an area here. The p-value is the area to the right. It's a right-tailed test. So the p-value is the area to the right of the test value. So the p-value is the area to the right of your test value. So I can see here, if I'm looking at area comparisons, that p-value area is bigger than my alpha area. So the reason it's bigger is because 305 is over here. So getting the visual here can show you that because your p-value is bigger than alpha, it means that that 305 is not far to the right. So it is not a significant finding. We're not going to reject the null hypothesis. So before I even write down that area, that p-value, I can tell visually here that my p-value is bigger than my alpha. And when I say greater, I don't mean it's to the right or to the left. We're talking about the size of it. So the p-value area is bigger than the alpha area. All right, let's get the actual number though, and we'll just confirm that. So the calculator gave me the p-value. They said 0.2991. So we're going to stick with our 4 decimal places for probabilities. So 0.2991. And I like to write that as a percent, 29.91%. So that p-value, you can just say p. I'd like p-value because we use p for population proportion. We'll get to that again in a bit. But p-value, calculator says p, that area is 29.91%. So my visual was right. That p-value, 29.91%, is a bigger area than 10%. So 29.91% is bigger than 10%. So when your p-value is bigger than your alpha, it means do not reject the null. Do not reject H naught. When our p-values are big, it means that our test value, our X bar 305, is not far to the right. Okay, so when you make a decision for the traditional method, it better be the same decision as you would make if you had used the p-value method, because we're just doing the same problem in 2 different ways. All right, so anytime your test value is not in the critical region, so it's not out here, that guarantees your p-value area is going to be bigger than your alpha. And both of those things lead to the decision, do not reject the null, do not reject the null. All right, so the conclusion would be the same regardless of method. If you do not reject the null, then you don't support the claim. And so that's our final summary there. So there's our conclusion. So at a 10% significance level, and based on this sample data, now there is not enough evidence to support the claim that the population mean is greater than 300. So this outcome was different than when our X bar in the previous problem had been 320. So the larger the p-value, the less reason to doubt the null is true. So the bigger the p-value, the less likely that we're going to have a reason to doubt that. And therefore, we don't reject it when we get big p-values. All right, and then we'll move on to some examples other than churros.